Nelson, and he worked on vortices and curved geometry. He did a postdoc at Berkeley with Ashby, and then went on to become a faculty member in Amsterdam University, Johns Hopkins University, and then we managed to persuade him to come over here and join us. He works on many different areas, cold atoms and spin chains. He worked in condensed matter. He's very famous for his work on topological phase of matter, especially the wild semimetals, and then some stuff that's related to his talk today, which is classification of entanglement in quantum systems, working with also with Ellisberg and Frank Pullman. And he worked on soft matter, jamming, with Vincenzi Vitelli. In other words, has a lot of interests. And I'm very happy to have him give a Blackwell talk here. Most important thing will be the microphone. So let me set it up so we can hear you.
So I'm going to talk about basically about zero-point motion and giving a precise meaning to zero-point motion in a many-body system. So, like, the idea or the question is that if I just have an atom, like a hydrogen atom with one electron, you sometimes say there's zero-point motion because even in the ground state, the kinetic energy isn't zero. But then you can say, well, that's because the classical picture, compared to classical picture, we'd say there's motion. But it's because we're using the wrong language, maybe. We're using classical ideas, and that makes us think there's motion. Because if you just look at a wave function of that electron, it doesn't evolve in time. So then you say there's no zero-point motion if you look at the electron. But if you start to look at many-body systems, you can start to feel more that there really is some kind of zero-point motion. And you can even give it a precise meaning. So the example I'm going to talk about is just a simple example of a container with electrons in it, for example.
I think you forgot one.
So these are all the electrons in the box. And imagine the ground state of those electrons. So it's a single state, which means it's not evolving in time. We know that. But you can ask a question. You can divide the box in half and say how many electrons are there in each half. And it's not a well-defined answer, or it's not a unique answer. Every time you measure it, you get a different answer. Because the number of particles doesn't commute, the number of particles in half the box doesn't commute with the Hamiltonian, so the ground state won't have a definite value. And each measurement will give a different answer. So let's try to guess or to understand what are the fluctuations of the particles. That's a way to this is a question you use to understand all kinds of fluids and things. Like if you have water, you can, what? Well, of the particles. If you have water, like you can measure the correlations of the molecules of water, and you get some kind of a curve that tells you how close they are to each other. So that sort of captures the behavior of the order. And we want to just capture the behavior of the electron. So let's try to answer this question. And to do that, I'm going to start with a simple case of just one electron. So there's this wave function of the one electron. So what are the possible, if I measure the number of electrons in the left half, what's the possible number? 0 or 1. You either have 0 or 1. And what's the chance of each one? Half and half, because it's equal probability on either side. So now let's take 2 electrons. If you have 2 electrons, there's these 2 modes. So in the finite temperature behavior, you'd say these electrons are just moving around back and forth, and this is their momentum.
So are these electrons charged?
No, they're not interacting. Yeah. So this question is interesting even if they're not interacting for electrons because of the Fermi statistics. So I want to see if the motion is like, if they're really moving, you'd say each electron is moving around randomly back and forth across the box. So if I have n electrons and I measure the number of electrons in one half, it's just a bunch of independent particles. So what would you expect the size of the fluctuations to grow as a function of that? Square root of that. And it would have a Gaussian distribution. And if they were like frozen in specific positions, then you wouldn't have any fluctuations at all. So what do you think happens in the quantum ground state? Someone want to get? What?
It's always dimension dependent.
Yes, let's say that's true. Probably depends on the dimension for quantum systems. Let's take a simple case of a one-dimensional system. How would it depend on it? If you don't.
So what's the question again?
How does the fluctuations of the standard deviation of the number of electrons in half the box vary with the number of particles?
N to the power 3/2.
Well, it can be bigger than that. Or maybe 2/3.
It has to be a surprise.
Yeah.
2/3 is not a surprise.
Oh, that's what it is. So it is a surprise. It's not square root of it. Yeah.
So you say that somehow the fluctuations mean that the electrons are moving.
Yeah.
Well, does it matter then how long you wait between the measurements, or how you prepare the system?
There's sort of 2 questions. One question is how do you measure it? And the way I'm thinking of measuring is you get it to the ground state, and then you measure it. And then if you want to do it again, you have to get it to the ground state again.
Okay, that doesn't mean they move, though. I mean, maybe the first time they were not moving, and you prepared it to the ground state, and if that's picture, they're still not moving.
You always prefer the same ground.
Yeah, you're preparing the same ground state.
Same many body configuration,
Yeah.
exactly the same thing,
Yeah.
or the same wave function.
Yes, the same wave function each time. So,
I don't see why that means they're moving.
well, I mean, you'll sort of see the way we're going to derive it, or to understand it, will kind of give a meaning to the idea that they're moving. The experiment itself, you could say, well, it's just quantum, whatever. But we're going to understand it in a way that really looks like the motion. So let's start with just these 2 electrons, and try to figure out what's the probability for the 2 electrons to be on opposite sides. So for example, what's the chance that electron 1? Of course, you're not supposed to say electron 1 and electron 2. You could say they're a spin up and spin down electron in an anti-symmetric state. So it's the same wave function, but you can distinguish them. You have electron 1 and electron 2. And what's the chance that that's on the left and electron 2 is on the right? So, because of the exclusion principle, one is in one state and one is in the other state. So you'd say, if electron 1 is in this state, you may say, if
So they don't have opposite spin.
no, they can have opposite. They're a triplet state of the
Okay.
Yeah. Yeah. So you have electron 1 in this state, electron 2 in this state, or vice versa. And if electron 1's in this state, it's 50% chance to be on this side, and 50% chance for electron 2 to be on that side. And they're independent, so you get a quarter. But that's not right, actually. And the reason is because these wave functions, you can't decide which electron is in which state. And after deciding which electron is in which state, decide which is on which side of the box. Let me write down the wave function. You'll see that. So here, x and y represent electron 1 and electron 2, and phi 1 and phi 2 are the two wave functions. So if I fix the position of electron 2 to be on the right side of the box, my first intuition was that once I fix that, this tells me just think of this as a constant, because I'm fixing y. My first intuition was that x is either in phi 1 or in phi 2, and each of them has a 50-50 chance to be on either side. So electron 1 has a 50% chance to be on the opposite side of electron 2. But that's wrong because this phi 2 of y is a negative number and phi 1 is a positive number. So these two functions they have a minus sign in front, they get added to each other, basically. With a certain constant. And that gives you an interference pattern. And so when we add them together, these have opposite sides here, so you get, if I square it, I get like a 0 over here on the right side of the box. So electron 1 is more likely to be on the left side of the box. So I can say it in a sort of simpler way. That it's not allowed to so you can't So the way you can say that is these two wave functions aren't orthogonal to each other. So I can decide. I can say first, like, is this electron 1 in this state or in this state? Because they're not orthogonal. They were orthogonal originally, but now we're looking at them just in this half of the box. And then they're not orthogonal anymore. So then you're not allowed to ask the question whether a particle is in one of two wave functions that aren't orthogonal to each other. So in other words, I tried to get the probability by breaking it into two cases. Either the electron one is in this wave function or it's in that wave function. And in each case, and then I just add up the probabilities in each case. But those aren't distinguishable possibilities. So I'm not allowed to break them up into those two cases. So now if you have many and it makes sense that so it makes sense that electron 1 is more likely to be on the opposite side of the box from electron 2 because of the exclusion. Basically, this 0 that I said was from interference. You can also think of it as just the Pauli exclusion principle. It doesn't want the two electrons to be at the same point. So now if you have many electrons, they'll have a whole bunch of wave functions. If I have n electrons, there'll be n wave functions like that. And if I want to know the probability of a certain number of electrons on the left side of the box, I could do the same thing I tried to do here and fix. If I want to know the probability that there's L on the left side of the box, I can fix the positions of n minus L on the right side of the box, and then go through all possibilities for what L wave functions these electrons are in. But those wave functions, once you look just at the left side of the box, they won't be orthogonal, and you have very complicated interference, and it's hard to figure out the probabilities. So the problem here is that we're trying to look at these modes and put each electron in one mode and then pretend the modes are independent of each other. And if that were true, then each electron would have a 50% chance to be on either side of the box. And you just get a regular binomial distribution for the probability of a given number of electrons as a function of L. The probability distribution will look like this. That goes to square root. But the modes aren't independent of each other because once you just look at half the box, these aren't orthogonal wave functions. So it turns out, it turns out the fluctuations, the standard deviation, goes as the square root of log n, not as the square root of n. And I want to understand the reason for that. So it's actually not too hard to just calculate that answer, because I can calculate, if I want to calculate the fluctuations in the density in this region, or the fluctuations in the number of particles in this region, the number of particles on the left side is equal to just the integral of the density on the left side over the left side. And then I can calculate the variance by just squaring this and taking the average. So it's proportional to the correlation function of the density. So let me just draw a picture instead of the equations for this. If you have just a gas of independent particles, like an ideal gas, this correlation function looks just like, and if you have the position of, as a function of distance between the two particles, there's a delta function when two positions are equal to each other, and otherwise there's no correlation at all. That's for a classical ideal gas. And what that means is that when I calculate the correlation, you'll only get one contribution. X and Y will just set equal to each other, and you get something proportional to the volume. But on the other hand, for a Fermi gas, and then you take the square root to find the standard deviation, so because it's the square root of 12. For a Fermi gas, the correlation is this this function that comes from integrating, basically taking the Fourier transform of the Fermi sphere, which the electrons are distributed over. There's a delta function in the center, and then there's a hole, which is because of exclusion principle, basically. So that means anytime there's an electron here, there's a missing spot around it. So the electrons are basically like rigid balls that are just packed really close to each other, and there can't be any fluctuations. So if you integrate that, you almost think you get zero fluctuations, but because it's decays slowly, you get some contribution near the edge to get the logarithm. Okay, so that's the simple way to find the answer. But I want to do something closer to this answer where I have independent modes, and I just think of each electron moving back and forth and has a certain chance to be on each side. So I'm going to take some inspiration from relativity, if you don't mind. So just forget everything I talked about. For a second, it's a completely different device. So, as you know, if you have a black hole, well, I don't know from personal experience, but it gives off black body radiation, the Hawking radiation. A black hole gives off black body radiation, and there's another effect that's similar to that, which is more, I don't know, less scary because it doesn't involve black holes. If you're in an accelerating reference frame, so if you're accelerating at a constant rate, then to you it's as if there's a gravitational field. Just like if you're an accelerating car, you think there's a force pushing you. So if you're in an accelerating reference frame, you may think there's a black hole somewhere behind you pulling you back, and that's the reason for the force. And in fact, there's sort of a consistent picture, because in accelerating reference frame, there's also radiation. So in accelerating reference frame, there's the Unruh radiation. So I'm accelerating, say, in this direction. If I have a detector for photons, I'll see photons every once in a while. So that seems like a paradox, because I'm imagining that I'm accelerating in a vacuum, so there's no temperature or anything. But according to this theory, in my accelerating reference frame, I see photons. And in fact, the temperature of the photons is 2 pi 2 pi times the acceleration is the temperature in units where A, B equals h bar equals the speed of light equals 70. And then I have to put okay, so that's a nice result. But it's very paradoxical and wrong-sounding result. Because how can you have a temperature when you're in the ground state of the system? So the answer to that is that in a quantum system, you have entanglement. So even in a ground state, of a quantum system. It's a definite state, but if you look at part of the system, it's not in a definite state anymore. So for example, in that case of having one electron in the box, if I look at half the box, there's either one electron here or 0 electrons here. And if there's one electron here, then there's 0 electrons on the other side. So you basically have a superposition of these two states. So you could say it's sort of a silly way to think about it, but you can say that the two halves of the boxes are of the box are entangled with each other. So they don't each have a well-defined state. And that's a much more general thing. If you have a spin chain with electrons with spins and the spins are interacting, then they try to form singlets with each other, and you end up with an entangled state. You don't just get a simple state where the spins alternate up, down, like you would have classically. So this is a very common thing to get entangled if you have an interacting system. So that means if I look at this half of the box, I'm going to get a different state every time. And it's not because I'm choosing a bad operator. It's not because I'm choosing particle number, and particle number doesn't commute with the Hamiltonian. As long as I'm looking at this half of the box, there's no basis I can choose where I'll always get a definite state. And the way you can make that more precise, or the way you can prove that, basically, so I can define a density matrix, the reduced density matrix, by taking the state of the whole system, make a density matrix out of it, and then forget the other half of the system, which means to take the trace on that side. So if I do that to this wave function, let me make this wave function a little more interesting. I'll make the electron a little bit more likely to be on one side. So then when I take the trace, I end up getting 2/3 probability to have one electron on the left and 1/3 to have no electrons. And that's not a pure state. If you diagonalize it, it has two different eigenfunctions. So it's like a thermal state where at a certain temperature, where this state has a lower energy than that state, so it's more likely to be occupied. So if you just look at half of the system, it looks sort of like the thermal state. And that, you can think of that as the explanation for the Unruh radiation. And the reason is, like here is maybe not clear at first, why does this have anything to do with dividing a box in two halves? But if you accelerate at a constant rate, there's a horizon. Like there's a certain distance where you can't get any signals beyond that distance, because it's neat actually, because you can't go faster than the speed of light. But if a light starts from far enough behind you, like by the time it takes a while to get to you, and you're going faster and faster all the time, so it just sort of gradually catches up to you, but you still can always outrun it. So what that means is that if I start accelerating at a certain time, then if you go to a distance that's 1 divided by the acceleration away from where I started accelerating, then I'll never get information from anything less than that distance. So everything I can measure in my reference frame is properties of the system to the right of this line. So it's like, to me, it's like I'm only looking at half of the space. So in my reference frame, I see a mixed state. So that's an idea also for why a black hole why a black hole theoretically has a finite temperature. The idea is that the black hole is a horizon and it cuts off part of space. So in the part of space that you can see, there's an indefinite state. which you can interpret as a thermal state. Basically, you don't know what's inside the black hole. That gives you energy. So I was looking at that clock for the same time, so I'm going very fast.
Because you're in the black hole.
Yeah. So now I want to try to solve my problem about the fluctuations of the electrons. So the way I can do that is I'm going to first make an approximation. In one dimension, you can think of an electron, of electrons as being relativistic, as long as you're close to the Fermi, close to the Fermi energy. They always move at the Fermi velocity, just like photons move at the speed of light, so it's relativistic. So close to the Fermi energy, electrons are relativistic. So that means that if I want to know the fluctuations of this half of the box, I can go to an acceleration. Suppose I can just choose some point. I'll choose some point which represents the observer, and I'll let him start accelerating fast enough that no signals will ever reach the observer from that point. So start accelerating. So I'll just assume he's at a distance of, this will cancel out the beat. So the observer will start accelerating at a equals 1 over r. And then just look for the fluctuations of the density in the reference frame of the observer. And the reason why that's a good thing to do is because since the observer is going at a constant acceleration, this is the state he's in is a time-independent state, so it just gets to a thermal equilibrium. So all you need to understand is the thermal equilibrium to the right of this horizon. So I just have to figure out the Hamiltonian in that accelerating reference frame, and I'm not going to write it down, but I'm going to just explain it a little bit. The eigenstates of the Hamiltonian, because since it's a stationary Hamiltonian, you have stationary states. The eigenstates look sort of like this. They start oscillating fast, and then they slow down gradually. And that's basically a redshift, because in this reference frame, there's a gravitational field pulling them that way. So as they try to get out of the gravitational field, their wavelength goes slower. And you can, and in fact, like the equation of the form of the eigenstate would look like the cosine of the log of x cosine of 2 pi times the log of x over r divided by the wavelength. That's the form. And the energy is just like what you usually have. The energy is 1 over the wavelength. In units for the speed of light, h is equal to 1. Oh yeah, it's yeah.
The speed of light or the Fermi speed?
What's that? Oh yeah, the Fermi speed is what I'll call the speed of light. The Fermi speed. What's that?
It's chi over r is really kind of the same.
Yeah, x.
X.
Yeah.
X. X.
Yeah, x times x.
I don't know.
Yeah. So this already wants to be right.
So it's really x times
Mhm.
yes.
Yeah. So then so by doing this transformation, we found what modes we should have been using before. We shouldn't have used the eigenstates of the real Hamiltonian, because the eigenstates of the real Hamiltonian are orthogonal to each other. The occupation numbers are correlated because of that. But what we should have been using is these eigenstates of the entanglement Hamiltonian, because because we have in this reference frame this reduced density matrix of looking at the 1/2. It's just the thermal state of that entanglement Hamiltonian. This is just e to the minus h over kg. If you just look at the 1/2. And that means each energy eigenstate is independently occupied from all the other energy eigenstates.
Why do you talk about eigenstate in an accelerating thing?
Well, if you're accelerating at a constant rate, in your reference frame, there's no time dependence. You just feel a constant gravitational field. Yeah, in the moving frame. That's sort of the trick. That's why the wave functions come out different. Because it's actually eigenfunctions of different Hamiltonian. This accelerating Hamiltonian. So it's actually a kind of complicated combination of the momentum and the energy. Gets you that. Transformation. So now each of these modes is independently occupied, and we can just use the Planck distribution, not the Planck, Fermi distribution, and the probability of one of them to be occupied is just equal to this, and they're all independent. So the standard deviation is just going to be the sum of the standard deviations of each mode, which comes out to be, doesn't matter. The answer doesn't matter. Conceptually, what's important is that there's just one term for each mode, and these terms decay to zero when the energy is very positive compared to kT, or very negative, meaning very below the Fermi energy compared to kT. So this sum just goes as kT, because that's the width of this distribution that we're summing over, times the density of states. That's the number of states within kT of the Fermi surface. And to see the density of states, we can just go back here, and we can say this is almost, if I just change the variables and call the numerator u, this is just cosine 2 pi, except for the 2 pi, which it's just a regular cosine, which means that these waves are just cosine waves in a box, but the box's coordinate is u, which goes as the log of x. So the length of the box is log of L over R. That's sort of the right end of the box. And then subtract the left end of the box. And for that we need a cutoff. So we end up getting log of L over cutoff. Otherwise you have infinitely many fluctuations at really short distances. So the length of the box goes as log of L over A, and that means the density of states.
No, A is not the acceleration.
Oh yeah, sorry. Let me call it. Let me call it D. So then the density of states is just going to be, it's a one-dimensional system, so the density of states is independent of the energy, and it's just equal to the log of L over D, the volume of the box. So that's where you get this logarithm from that I talked about at the beginning.
You need a square root of that.
Well, that's it. Oh, sorry. This is this standard deviation. This was the variance with them. I left out a small, I made a small mistake because I had this R factor here. So the length of the box is actually R times the log of L over D, which is important because I now say R is 1 over the acceleration, and the temperature by this Unruh effect is 2 pi times the acceleration. And then the acceleration cancels out. So that gives me the fluctuations in the box.
Yeah, we could probably gotten it without talking about acceleration. Calculate it correctly.
Well, you can calculate directly from the correlation function.
Okay.
But the nice thing about this, there's sort of two nice things. One is you can generalize it to interacting systems. But another, the specific thing, is that you can use this method to calculate not just the standard deviation, but the probability distribution for different numbers of particles. Because what this tells you is that each mode is independent of every other mode. So you just have a bunch of independent modes which have a certain probability by the Fermi distribution to the occupied box, and it'll add up to a Gaussian distribution. So you see you get the distribution. In this case, it's not so insightful, it's just Gaussian. But you can actually, there's actually other cases of spin chains where you don't get a Gaussian distribution. You get other distributions.
Sorry. How does the position of the where you cut your box? So if I could put it, let's say, 3/4 of the way. How do I change?
Well, as long as you put it closer to this end than this end, it doesn't change too much. But if you put it really close to this end, then because the two ends are correlated, it's the small end that determines the size of the fluctuation. So I can't actually see that from my argument because I did kind of a rough thing to the end. I just kind of I put a wall, but I put a wall in my accelerating reference frame instead of in the original reference frame. That's a little bit wrong to do that. So it becomes more rigorous if you have a state that actually has a finite correlation length. And then you can use an infinite system. And then because in an infinite system you still have a finite amount of fluctuations in that.
I'm a little bit confused about the limit of this expression you wrote.
Yeah.
Suppose, I want to look back with the full bones. So that would be like acceleration, your effective acceleration going to 0, right?
You're saying because you're...
So suppose, I'm not looking at half and half, but 1 and 0. So
Yeah.
the product should be 1.
Right, but you shouldn't have any fluctuations.
Right?
You shouldn't have any fluctuations.
No fluctuations.
Yes.
Right, but R is 1 over A, right? I mean, your R is 1 over A.
Yeah, so I mean, it doesn't work. There's something fun, that's what I was just saying. There's something funny about this approach in the finite box. Because I'm using to find the normal modes in the accelerating reference frame, I have to put a boundary condition at the end of the box. But that boundary condition, if it's in the accelerating reference frame, it's sort of like accelerating with you, and it's actually changing the problem to put that accelerating boundary condition. So that's not really justified. But what you can do is if you have like a small gap, like if it's a superconductor, it's a small gap, then you can look at an infinite size system and divide it just into two infinite halves. And then you can ask what's the fluctuations in each half, and then it'll be a finite answer because of the gap. And then you don't need to put a boundary condition. So in that case, you get, it's more rigorous in that case. So, I'll just give a little bit of general.
You can raise the board.
Oh.
Second bring the other one down there.
So, so suppose we have, so if you have any many-body state, any system at all, you can always divide it into two halves. And I can just, in this case I got a Hamiltonian by using this Unruh effect. But you can actually, in general, if I have a many-body state, I can define the reduced density matrix for 1/2 from the ground state wave function. And then I can just take the logarithm. I can just choose a Hamiltonian, choose the temperature kind of arbitrarily, basically to define the units, and then find a Hamiltonian such that this is true. So you can basically simulate, you have quantum fluctuations, but you can simulate them by choosing the right Hamiltonian. So in other words, I'm just taking the logarithm of the density matrix, and I'm taking minus kt times that, I'm calling that the Hamiltonian. And it's a Hamiltonian that describes, it doesn't describe actual dynamics, because it only depends on the ground state wave function. It doesn't have anything to do with the dynamics, but it's interesting and it has nice properties. And at first you might think it's really terrible because the logarithm of a many-body state, of the many-body density matrix, will have long-range interactions and every spin interacts with every other. But at least in the case with relativistic symmetry, this argument shows you that it's actually a local Hamiltonian. And people have done sort of numerical calculations for just non-relativistic systems. And a lot of times it seems to have short-range interactions too. So that's neat, but does it have any physical meaning? And one thing before figuring out what the physical meaning is, one thing we can kind of guess about it is that all the couplings in the entanglement Hamiltonian, if this is the region we're focusing on, all the couplings in the entanglement Hamiltonian grow as a function of the distance to the boundary, just like that. Like the coupling maybe grows linearly with the distance to the boundary. This is kind of equivalent to the redshift of the wave function before. So if that, and the reason that happens is because the entanglement is strongest over short distances. So things that are really far from the boundary don't fluctuate too much in entanglement Hamiltonian, which means they have a higher energy. So if you look at this, if you create an excitation of the entanglement Hamiltonian, the excitations cost more energy in the middle than in the edge, so they would all be trapped near the edge. All the wave functions would be decaying exponentially away from the edge. That didn't happen over there for the electron, but that's because that's a gapless system. So it's a little bit. So anyway, so this entanglement Hamiltonian is kind of like a physical Hamiltonian, although it's not related to the actual Hamiltonian. But it could be something you make experimentally if you set up the right interactions, except that everything's trapped near the edge, so it's one dimension less than the physical system. And it's neat to say, like, if I have a state, what are the degrees of freedom? Like, how is the entanglement Hamiltonian different from the real Hamiltonian? And is there any correspondence between the two things? And it turns out, like, in topological phases, there's a really, like, there's a close correspondence. So if you have a fractional quantum Hall state, there's edge modes. And if you look at the spectrum of the entanglement Hamiltonian, you see that there's also edge modes in the entanglement Hamiltonian, and they have fractional charges. So the edge modes of the entanglement Hamiltonian have fractional charges. So this is a very useful thing for understanding topological phases. Because what is a topological phase? It's a phase, if you make a phase diagram, you have some kind of a phase boundary where nothing really changes. There's no order parameter that changes. And like that's what happens in the phase diagram for water, except for water it's sort of it's a fake phase boundary, because if you go up to a high enough pressure you can get around it. But in these topological phase transitions, there's a boundary off to infinity, and you can't get from one to the other, even though nothing seems to be changing in terms of order parameters, in terms of like the density or the symmetry or anything. And this entanglement Hamiltonian gives you a way to see that there's a difference. Because if you look at the entanglement, in one phase you'll have excitations with a fractional charge, and the other you have excitations with an integer charge. So that's neat, because before this idea, which came from a paper by Lee and Haldane, before that you might say, oh, these phases are characterized by having fractional excitations. That's what distinguishes them from ordinary phases. But that's an excitation. Why? That doesn't tell you that the ground state actually has to do something dramatic as you go from one state to the other. And what this shows you is that if you just look at the ground state has those excitations fluctuating around in the entanglement spectrum. So they're there in this. If you look at half the system and you look at the fluctuations of half that system, the eigenstates of that half have a fractional charge. And it actually, so that's a general and interesting question. What are the relationships between these excitations of the entanglement Hamiltonian and the real excitations? So that's it.
Two related questions about the analogy itself. So when you have, for example, in the case of Hawking radiation, whatever is lost is done into the horizon. So in the Box case, it seems that the wave function, in the calculations which you have, the wave function is then written back, which is different from the case of the Hawking radiation, because that's totally lost into the horizon. So that's my question. The second question is, if you measure the state of the system in one half, how much information do you know about the second half? And I'm asking this in relation to the loss of information for the black hole. Some people claim that you have all the information, Hawking radiation.
Yeah, I don't know how to, I don't know the answer. Like, if you're, I guess that's kind of the, maybe I can say the second question I can interpret as sort of an answer to the first. So the idea in this picture is that the reason you have a mixed state when you look at half the system is because each state is correlated to a state on the other half. So like an entropy of the one half is equal to the information that half gives you about the other half. So in that idea that the temperature of the black hole comes from entanglement, The idea is basically that the Hawking radiation is there because it's giving you information about what's inside. But yeah, but I like also the idea, like the questions, like, is there an analog of losing information behind the horizon? And I think, like, since I'm only looking at the ground state, it means I'm constantly accelerating. I'm never letting something go and letting it fall into the horizon. So that's why I don't lose anything behind the horizon. But maybe there's something interesting you could find out by thinking about what happens with it.
Questions?
Yeah, that's a very good question.
What do you answer that?
Should I repeat the question?
So, Ali is sticking around, or you can ask him whenever you like. Thank you very much.